Good morning.
Hey, good morning.
Good morning.
Hannah, you are the smartest one of all of us. You are outside.
I am.
Martin is here. Martin, what do you need from me? Are you all squared away?
Not yet. I have to pay off the stupid spring stuff, but my advice, I don't know. I paid it off, but it still says I'm on like a hold. So I didn't sign up for the My Open Math yet, just in case.
That happened to my friend too.
Just sign up for it, Martin, and get going. If it doesn't work out, it doesn't work out. But my open math is free, so just get in there and get going. Just join the class.
Okay, I got the book from they had a copy at the library, thank God. So I'm set. I'll get it rolling like financially, I guess.
Yeah, well, don't worry about that. That'll take place down the road. But get in my open math and get going.
Got it.
The homework is straight out of the book in this class, not coming from my open math though. So, but there's a lot of stuff in there you need. So,
Got it.
Hannah, are you at your house? That's paradise.
Yeah, I am.
That's awesome. I love being around trees. Trees are the best. Trees. I go kayaking after class every day, so I can be in the forest. Well, let's see how many times the old computer will die today. All right. Today we tackled separable differential equations, which I've already hinted at. So we're not going to suffer much today, I expect. Oh, great. We're already turning black right at the start. Let's see, I'm going to try putting this over here, minimizing that so I can see all of you.
We can see your note now.
Good deal. Separable differential equations. And so let's just dive into something kind of cool right now. I just happened to mention that I go kayaking after class every day. And one of the things I'm always looking at every year is the Illinois River. Right now it's too low to run, but we do a overnighter on that a couple of times, usually like in April, May, June, somewhere in there. And I'm always kind of watching the levels, and that's kind of my job as the math nerd, is to, we're always trying to, set a date, say 3-4 weeks away or something like that. But the question is, will there still be enough water in it? It's always kind of dropping. And I'm not going to take the time to pull up some of the stuff I've done, but it's like, it'll kind of, drop like this. And we're always kind of looking for the 250 number. In other words, we don't want it to get below 250 cubic feet per second, because then there's enough water to get over the top of the rocks and stuff. And so it's always kind of a question of, you're here right now, but then, this is the launch date out here. And so it's always kind of a question of, what's the flow going to be on that day? Is that going to work? And so forth. And so this is one of the classic models, one of the easiest introductions to, and I already hinted at this a little bit in another place, if I remember right. But this is one of the easiest introductions. And so let's just say, okay, to keep it simple, let's say the river was at, I don't know, 850 on whatever, May 2nd.
I don't see any writing.
Yeah, we just see 2.2 separable ODEs.
Really?
Yeah, it hasn't moved.
Updating live to me. Tell me when you do, because it seems like it's working on my end. I'm going to reshare. Stop and reshare. Thank you for speaking up quickly so that we don't waste our time. So we'll say that the river is at 8:50 on May 2nd. And we'll say that it drops to
Now it's
say,
working.
now we're back.
Yep.
Oh, it doesn't like it when it's on that screen. Gosh, man, this thing is such a pain. So then we'll say it drops to, I don't know, let's say 765. So it drops to that on May 3rd. So let's say that's the only information we have. And many things drop kind of by, you know, some kind of an amount. And because naturally being a river, this thing is going to kind of level off. So, you know, if you kind of do the subtraction, 850 minus 765, you get, I can't type and I don't want to do it in my head for some reason this morning, lazy. You get 85. So this basically dropped. Why is it not going to just keep dropping 85? In other words, a constant rate of change. Why is it not going to do that? Because of nature. Why would that not make sense? And I don't think that's necessarily obvious, but if it did drop 85 a day, does it make sense? That's what it would do. It's actually dropping linearly, 85 every single day. The rate of change is 85. In other words, you would say that, let's see, I'm going to say L for level. So we'll say that's level. So DL dt equals 85. And I guess we should even say negative 85, right? Because it's dropping, not increasing. It's not going up. And again, that's a very easy differential equation to solve, because if you multiply both sides by dt, then you could take the integral of both sides, and the integral of 1 with respect to L would grow an L. The integral of 85 with respect to T would grow a T. And again, technically there'd be a plus C on both sides, but we would combine them so that there's just one C on one side. And so notice that creates a linear equation. The slope is negative 85. Y equals mx plus b. The slope is negative 85. Yeah, that makes sense, right? Because that's what we wrote in the first place. Like, that's what the slope is. It's a rate of change. And so if that was a constant rate of change, that'd be the case. And in our case, if we call this effectively T equals 0, notice that's not time 0 like BC, AD before Christ and so forth. That's just like when I started paying attention to it. Does that make sense? Like, that's the first day I looked at it. I could have said that's T is 2 just to keep it simple, and I often do that. I think I will right now, just because I don't have to think so hard. In other words, hey, it's May 2nd. I might as well call that day 2 instead of day 0. So then I could go in here and say, okay, well, the level was 850 when the time was 2. And so what does that mean C is? And so I'm adding 170 and managed to write that down correctly. So I'm adding 170 to 850, which of course is, I guess I could do that in my head, 1020. So then you could say the level as a function of time. You can add that little L as a function of T. Remember, that was Euler's contribution to functions. That's the way that you say this. And it's kind of a cool thing to say, rather than just say L equals, say L is a function of T, meaning what I'm going to see on the other side of this equation is just a bunch of T's. Making a lot of mistakes today. So then that would be our function. And so that's why I drew that red line over there. So the reason that wouldn't be realistic is because that's just not what rivers do. They don't run out of water the same amount every day. They, as I hinted at earlier, they actually kind of they level out, they slow down. They don't just run out immediately.
Is that because of the shape of the bottom of the river? Maybe that you lose a less, if you lose the same number of inches vertically every day, then you wouldn't necessarily lose the same volume of water. But I don't know. That's just a guess.
Yeah, no, that's good. I love that. That's exactly what we're doing. I'll give you an example that I think has to do with it. Have you ever walked up to one of these drink containers that has a little spigot out of the bottom of it, like at a wedding or something like that? Have you noticed that when this thing is full, that the liquid, the lemonade or whatever, just rages out of the bottom of it, comes out really fast. But then when the liquid is down here, it just kind of puts out the bottom, doesn't come out very fast.
Oh, because there's less pressure.
Exactly. So the weight of the water pushing down at the hole, which is at the bottom of the drink container, is pushing really hard. It's kind of the equivalent of somebody pushing down on the top of it. So it rages out the bottom. But that rate as it goes out just gets slower and slower and slower. So technically, if you want to sound really smart, you say that's hydrostatic pressure. Hydro is water. Static means it's not, moving. It's just the weight of it, and then pressure. So hydrostatic pressure. So I think that has something to do with it. So you imagine, the mountains are full of water because it's been raining, and the water is leaking out of the mountains down into the creek and so forth. And so that doesn't just leak out linearly, if you will. So that's kind of complicated. I mean, I would say I don't totally understand that, but I think what I just showed you about hydrostatic pressure weighs into it a little bit. So what's more realistic than kind of this model? What's more realistic than that? Well, a little more realistic would be to say, well, we dropped 85 CFS, and we got kind of lucky that I happened to make that up. Does it make sense? 85 is 10%. In other words, we lost 10% of it. So I didn't have to bust out my calculator and figure it out. It was just kind of obvious. 80% of 850. Well, if that's the case, then what is, and I'll let you think about this for a second, what is the differential equation now? What would because again, what we're talking, the only thing we have access to, and this is the beauty of differential equations, the only thing we have access to is, hey, things are changing. Does that make sense? All I know is how it's changing. The first time I said it was changing by negative 85, and that produced a line. That's all I knew. And thanks to, the ability to write and solve a differential equation, we actually found a model for that, which is kind of neat. Well, now we're going to look at it and say, well, it's actually more realistic that it's 10%. Now think about this because it's kind of cool. 765, when you take 10%, I'm going to erase this, I think, but when you take 765 and you multiply by 10%, notice you only get 77 cubic feet per second. In other words, the first day it dropped 85, but then the second day it only dropped 77. You see that? And that would kind of fit reality here in the sense that it's going to level out. So I'm losing by a percentage, not by a fixed amount. And that's super common. Like, you look at a town and say, what's happening to it? Well, it's losing 10% of its population, or it's increasing at 9%. Things increase and decrease by percentages all the time. That's a very different, model, if you will. And so what would that differential equation look like? Well, notice I took 10% of the actual level. Well, this is what it would look like. And in a sense, if you want to really be good at differential equations, this is the kind of thing you want to actually model things in the world. This is what it would be. it wouldn't be this. This might be what you would think. But notice it's not just 0.1, it's 0.1 times whatever the level is. Does that make sense? That's what I just did a second ago. Didn't I take 10% of that level? What's wrong with that?
We have L on both sides.
That's okay. I don't want it there. To your point, Connor, I wish it wasn't there. Last time it was just a constant 85, negative 85.
L's just always changing, right? Like L would be different every day.
That's exactly right. L's different every day. So it's going down, down, down. But the key is it's going down, 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 not up, up, up. Its rate of change is not positive 0.1, it's negative 0.1. Does that make sense?
Should we use Euler's number?
Yeah. And so, and I guess I want that to sink into you. Does it make sense that the rate of change is losing 10%? Well, 10% of what? Well, 10% times whatever that level is, but unfortunately that level is changing every single day. That's why I need the L in there. Does that make sense? This wouldn't make any sense if you said there's your differential equation. Because if you said, dude, you have 10%, the automatic question is like 10% of what? Hey, I'll give you 10%. 10% of what? 10% of all the money I find on the road today. I'm not that interested. 10% of all the money I've ever made in my life. Oh, well, now I'm pretty interested. You see what I'm saying? Like, it doesn't make any sense unless there's kind of an L there too. Well, that's very different than the last differential equation, because the last differential equation just had a constant over there, and that was okay. If I said the river was dropping at 85 cubic feet per second per day, that's all you need to know. There's no L over there. Now there is. Well, again, this is a separable differential equation, which I've already hinted at. In other words, I can do what I did up here and actually get all the L's on one side and all the T's on the other. Notice I don't have any T's in this particular one, but I can at least get all the L's on the other side. And so this would, if I divided both sides by L, and this is something I played with you before, and I multiplied the dt over to this side, now I am free again. Now, because I was able to separate them, separate the L's and the T's, then I can actually solve this. I can do what I've been wanting to do from the start, which is take an integral. Again, you understand the logic. I'll try not to repeat myself too much, but until you, just to make sure you totally get this, I don't want this equation. This is awesome. It's amazing that I wrote it. It's the only access I have to the problem, but that's not what I want. I want an equation L as a function of T so that I can figure out, well, you know, our trip, I checked these first days right here, but our trip is planned for, say, May 21st. And really what I would like to know is what's that level up there, right? Does it make sense? I need a function for that. I don't want a derivative. I want a function. The only accesses I have is an equation with a derivative in it. Okay, well, I don't want that derivative. Well, then take an integral. That's what the fundamental theorem of calculus says. Well, we're doing it. We're taking an integral. What's the integral of 1 over L?
Natural log of L.
Natural log. And the integral of a constant just grows a t. Again, there would technically be a plus C1 and a plus C2, and you're beginning to realize how important that is in differential equations. But really what I would do is add that to the other side. So I just have one constant. There's no reason to have two. So I subtract that C1 over to the other side, and then together that would become some kind of new C. So just to save a little bit of time and thought, like that would be my equation. Now, is that equation useful?
Not quite.
Correct, not quite. It's not useful because, well, in the language of yesterday, it's a family of the last couple of days. It's a family of solutions because that C can be anything. And so I would get a direction field of all different kinds of answers and so forth. And so it's not useful until we come back and say, hey, I did happen to know that the level was, and let's do this. I did happen to know the level was 850 when T was 2, right? So I got to plug that in, and then I'll know what C is. Now, I want to do one thing that's kind of a little creative here first, because notice this particular equation is, well, implicit, right? It's not solved for L, and it'd be kind of more useful to me if it was solved for L. Well, you know how to do that. You would say, all right, well, then I'll raise both sides to the E power. Again, I did this the other day, but I just want to go kind of slow here. Do you understand that that's the same thing as e to the negative 0.1 t times e to the c? Don't you add exponents when you multiply? In other words, x squared times x cubed, isn't that equal to x to the 5th? You add exponents, right? Well, I just went backwards, right? There's a couple of exponents being added, so I just went backwards. And if this is just a constant e to the c, does it make sense I could just rename it as some new constant? And again, just to keep it clear, I'm going to call that C1. So kind of the best way to write this is L equals C times e to the negative 0.1 t. And again, I said this the other day, but you should recognize that. You should say, hey, that's the classic exponential growth function. But the key is, where did it come from? Well, differential equations is what made it. It wasn't, I mean, you and I were kind of under the impression when we saw this in Math 111 and other places that, you know, some smart person, you know, how do you know that's the case? Where did that come from? You probably didn't even get an answer to that question. Well, it came from differential equations. Notice how it started so simply, so beautiful here. It's just that's such a nice statement. The rate of change of the level is dropping 10%. The level is dropping 10%. Like if you said that in English, all you're doing is writing it down. Except because of the knowledge you have, we're saying, hey, I can do something with that. Now, this C, if you solve this as I did earlier, kind of back here, we'd get a different C value there, but this is a nice place to put it. This is a really nice place to put it. But now is when I'm actually gonna plug stuff in. And so I know that when L is, so I have a whole family of solutions here. By the way, let's just do this really quick because we can. Let's see, I want to see if Desmos will let me, no, I don't want to, yes I do. Let's see if Desmos will let me do this with the same letters I was using. I was kind of curious if it would like that or not. So we have C, and it knows what E is. And now I say raised to the power of negative 0.1 t. Notice it doesn't like that. See how it wants t to be a constant, and it's like, no, that's not a constant. It doesn't like that. I wonder, actually I don't know the answer to this. I wonder if I went back to the start and I said L is a function of t, then would it like it now? Oh, it did. That's kind of cool. So I was telling it t is my independent variable, right? I'm telling it, hey, t is my independent variable. And now it's saying, okay, all right, I'll do it now. Notice that's doing what we said it would do, which is dropping kind of slowly. Notice if I mess with C, can you see the direction field this would have produced? If I went into that program and did that, maybe I'll go do that in a little bit, but so notice can you picture what the direction field is going to look like just based on the fact that I'm showing you the whole family of solutions? Notice no matter what, you're going to have no water here. If you lose 10% of something, you're eventually going to run out of it. So do you see how it's exiting the stage over there at 0 when X is really large? The time when T is really large, you're going to have no no level, no matter what you start with. Of course, down there is kind of weird, right? It's like you came from underground or something. So really the problem only makes sense up here. Notice that's an interesting case. If you start with 0, then you're just going to have 0 from now on. But this is how things work when they drop by percentages. And so that's not that surprising. Cool. So I say, all right, I need to actually know the particular solution when t is 2. Are you good at solving this? And by the way, do you notice how much easier this problem would have been if I picked t as 0? That's why oftentimes the the book will talk about things as initial conditions, because if t had been 0, that would have been e to the 0, which is 1, and that means c would have actually been 850. And you may have memorized from earlier in Math 111 that this number was oftentimes called the initial amount. Sometimes it was even changed from c to like L0, meaning the initial level. It was even called that. But I'm going to do a little more work now, because what I'd really like is to be able to stick 21 into my formula for May 21st and not have to think, oh, let's see, I want the 21st. Does that mean I have to plug in 23 or was it 19? Like, I don't want to be confused. So I'm going to have to work a little bit harder. Of course, this isn't hard, right? You just take e to the negative 0.2 power and divide it 850 by it. So I'm taking 850 in my calculator, dividing by e raised to the negative 0.2 power, and I get 1038.2. So my L as a function of t formula is 1038.2. I don't really know if I need the 0.2. I think I'll leave it off. E to the negative 0.1 t. And so I'm very excited now because now I actually have an awesome model for my river flow. Just to check my work, because this is one of the reasons I've been showing you this. You should not get stuff wrong and not know it. This is important. So if I go back here and say, hey, that number is actually 1038. Come on, man. Give me a 0 when I hit it. What am I checking here? How do I know that I got that right?
Falls within the slope field.
It should kind of line up with the slope field, but I have a better answer, a better way to check it. Isn't the point when the time is 2, isn't this point supposed to be on the graph? And there was another point, right? That point's supposed to be on the graph. Oh, good, look, it is. Now, how come this is dropping so crazy fast? Notice I'm stretching the graph so it doesn't look so terrible now. All of a sudden it looks okay.
Because 10% of bigger numbers is more drastic than smaller numbers.
Yeah, that's right. 10% is a lot. It's a lot. It's a huge number. Notice that's a much better window. So this is what I'm literally doing this every year. Now I don't write it as a differential equation. I know that c times e to the power, and I even use regression. I don't even do that. I cheat and stick in 3 or 4 ordered pairs and I have it find an equation for me automatically. But an exponential one like this is often a really good fit. Of course, notice now that you have this graph, you don't even need to use algebra to answer the question, what happens when x is 21? Notice I can go out here and I can type the equation, x equals 21. Gosh, every time I hit these buttons, it's not showing up. So notice our plan is in trouble because there's only going to be, at this rate, there's only going to be 127 cubic feet per second out there, and that's not going to be enough. And so You know, we're gonna have to back the trip up. I'm gonna have to, and of course, this is the kind of thing I would do, but this is what it means to speak the language of algebra. So I think it's good to, you know, waste a few minutes here and do that. It's frustrating. Notice that says you better make your trip by May 14th, because May 14th is going to be the last day that it's got 250 in it. So you better bump your trip up a week. Better start a week early. And I've been doing that river for 10 years now, and it's the kind of thing we do. We're doing that all the time. We got to bump it up, or hey, it's still going to be flowing a week after we're out, and so we can even put it off a week because the weather's bad. You know, it's rainy or something like that, or overcast. It's not very warm, something like that.
What's the rate that it usually drops at? Like around 10%?
No, that's way high. It's usually quite a bit lower than that, more like 4%.
Oh, wow.
Let's see. So of course, do you see the big picture? Like this, in one sense, you're done now with differential equations. You now understand what they are and what they do. I never really wanted the differential equation. What I really wanted was the actual function without a derivative in it. And now I own the relationship. And notice I can work backwards. This is kind of cool. I'm not going to do this algebraically. I just cheated graphically to do this. But of course, the first thing I'm going to do with this newfound equation that I have here is I'm going to go back and stick 21 in there, right? And we saw from the graph that's going to produce 100 and whatever it was, 37 or something. And so it's like, oh no, that's disappointing. Well, then the second thing I'm going to do is go over here and say, well, I need the level to be 250. Then solve for t. Does that make sense? Like that's why you studied all this algebra. So the question is, can you speak the language of algebra well enough to do anything with it? You understand the power of what a function is and why we, you know, need to take the integral to get rid of the derivative so that we can now use the function to answer interesting questions. It's a beautiful thing. Let's make this a little bigger just in case you want to look at it later. So cool. All right, so now let's let this kind of devolve into just practicing random kind of, you know, book created, not practical, but just kind of book created separable. So you can now, you have the concept of how to solve a separable differential equation. Quickly, I'm going to just do this. If I say dy dx equals x plus y, notice I got rid of the interesting letters L and T. You're not going to be able to solve that right now. I just want to take a second and get you to notice that. We don't like plus signs. If we're trying to use the concept of separable differential equations, we don't like plus signs. I just want to make sure you quickly see why. You won't be able to do this. We'll be able to do this next week. You might think, well, yeah, you can. This is easy. But are you able to separate them thanks to that plus sign? Well, you might say, yeah, I'll subtract y to the other side. And then I'll multiply by dx, just like I did before. Done. What's wrong with that, though? What algebra mistake did that person make?
You missed a dx. It needs to be multiplied by the y, or the negative y.
Exactly. You failed the distributive law. This also gets multiplied by dx. Notice it's not separated yet. And because those are multiplied together, they're hard to separate. If I divide by y, great, you divided by y, but now this gets divided by y. And so they're hard to separate. And they don't. Like, you cannot solve this when using the concept of separable differential equations. There's no way to separate them, despite the fact that it might look like you could. So that's the terminology side of this class. And I hinted at this earlier, but ultimately you need to be able to recognize different types of differential equations. So you can say, oh, that's separable, I'll use this technique. Oh, that's linear, I'll use some other technique. But let me give you an example of one that doesn't really look like it, but actually is separable. That actually will separate.
You
The
just have
reason
to
is,
factor out a y.
yeah, the reason is, and we saw one like this the other day, and I think this kind of came up, but the reason is you can factor a y out. Since they both happen to have a y, well, now you can divide both sides by y and multiply both sides by dx, and you got it done. You got all the x's on one side, all the y's on the other. So it doesn't just mean if there's a plus sign, you can't do it. So you take it from there. What's the solution to this? Notice I'm not giving you what mathematicians would call an initial value problem. I did not give you an initial condition. All you're going to get for this is a family of solutions. So you should say, like, before the integral of 1 over y is the natural log of y, the integral of 2x is x squared, the integral of 3 is 3x. Again, both sides have a plus c, but I think I'll just put the plus c on one side. You're done right now. You have done it. You've solved it. You're done. It's explicit. Maybe it's not as useful, but if nobody says otherwise, you've got rid of the derivative. You solved it. There it is. Now, what I'm anxious for, and I want you to be able to check your work. So make sure you're taking advantage of the technology that you have. And so let's do that now. Let's see here. Why can't I? So let's go graph this thing. Remember from the start, we already had kind of some cool tricks to do this. So we have 2xy plus 3y, 2xy plus 3y. Bam, usually you want the density to be higher. So here's your family of differential equations. And of course, it's nice to have one, at least one in here. And so notice you kind of have this parabola looking thing. And as it slides down, it sort of flattens out, and then it does the same thing down below. And so there's the family. So as I said the other day, none of us look at that and go, oh yeah, I recognize that. I know what that equation is. Notice I said equation, not equations. That's one equation. What we are saying is we actually just found it. We know what that equation is. So do we? Let's go to Desmos and graph what we just found. So I don't even have to solve it. I can say natural log of y equals, notice it's natural log on one side and it's like a parabola on the other side. Isn't that kind of cool? X squared plus 3x plus c. It's going to ask us for that constant. And sure enough, isn't that the exact same thing we just saw? Isn't that cool? Notice how do I get the bottom one? Anybody know how I get the bottom one? How come there's no bottom one? This is one of the technicalities.
Is natural log undefined below 0?
Yeah, it's because natural log is an absolute value. So I think if I put an absolute value on the other side, then I'd be able to get the bottom half of this too. I think that's the case. But isn't that cool? I mean, isn't that amazing that like this proves that it worked? We visually saw the answer here. We just didn't know what it was. And then we were able, in this case, to actually algebraically solve it, and we got the same exact answer. And so now, of course, we could proceed from there and get a particular solution to this if we wanted one, if we needed one. So that's kind of powerful. I want you to be. This is again why I assign few questions, because I expect you to be doing this kind of stuff, not just quickly answer it and then move on to the next one and be done. But graph it, play around with it, visualize it as a slope field, get into Desmos, graph it, kind of see that they're the same thing. You should not be getting this stuff wrong and not knowing it. That's the thing that's so cool and so powerful. You should have a chill running down your spine. Man, this stuff is awesome. This is amazing. This is cool. So sharing my screen again. So now let's go back just for the fun of it, since we're sitting here. Let's go find the initial value problem. In other words, if I went back and told you that y of 0 was equal to 4, now initial value problem. Do you see why it's called that? Initial value. I'm giving you an initial value. So if I told you that, would you be able to go ascertain what that constant is?
Are there absolute value bars around the y?
Yes, it's the y that they're around. When you take the natural log of something, it's actually the natural log of the absolute value of y. Again, that's you saw that was a semi-important technicality, but I'm not going to emphasize those technicalities just because I want to stay on the point. In other words, I'm going to give you full credit if you gave this answer and didn't notice that. It's kind of like saying, what's the square root of x squared? And somebody says x, and I'm like, wrong. It's absolute value of x. I'm not going to do that. It's true. You're right. The actual answer, that is the natural log of the absolute value of y. So include that. So of course, this isn't hard. This is just saying when x is 0, and notice we're always happy for the initial value to be 0, because notice it just means I don't have to do that much work. Then y needs to be 4. Oh, that's obvious. Then c is the natural log of 4. So now I have not a family of solutions, but a particular solution. And of course, I'm not going to take the time to do this, but if we were going to use this for something, of course, solving it for y, raising both sides to the e power and so forth. Notice that's kind of cool to think, what was that graph really? It wasn't e to the x, it was e to the x squared. Isn't that kind of neat? That's what it would really be. And if I solved it, I mean, there's more to it than that, e to the x squared plus 3x and so forth. But none of us know what e to the x squared as a graph looks like. That's why we didn't recognize it. It's just not that common. So we'll just leave it implicit. So again, that's terminology I've used a lot. I want that to go into your head now if it never has before. If I don't say on a test, solve it explicitly for y, or, I could say something like find y of x. Does it make sense? That's asking for it being explicit. If I said it that way, I didn't do that. It says natural log of y. I want to know what y is. So we have to do another step. Incidentally, just out of curiosity, I'll go ahead and write the other answer. It would be y equals, and you could either say e to the x squared plus 3x plus natural log of 4, or if you had started with c times e to the x squared plus 3x, since x was 0, that'd be e to the 0, which was 1, which would actually cause the c value to be 4. Isn't that kind of cool? So that's actually what the other answer would look like. So they're both fine. So no wonder we didn't recognize it.
So in this case, if we were to have undone the natural log, then we would have the absolute value bars there and they would become important, right?
Right. And so if I have absolute value bars here, then what I'm really saying is another way to get rid of those is to say this side could be plus or minus. And that's why there'd be a top and a bottom half to it. Does that make sense?
So we would include the plus or minus in our
You can.
solution.
It's good practice, but I'm not gonna emphasize that.
Okay,
I should.
cool. That's something I've just
I
always
know.
been a little confused about. So it's nice to hear
Yeah.
that it's not.
So that's kind of cool. So not only did we solve it because it was separable, we even were able to kind of check and say, yeah, I nailed it. Look at that. It's amazing. I can see the whole thing. Try this. This is again, just kind of a sterile book example. But it's going to look kind of like the problems that you're doing. I'm going to give you a second to think about this. And notice I'm messing with the letters. And it's always a bummer when x is sort of, you're used to x being the independent variable, and notice because it's on top of the dx dt, it's actually the dependent variable now, and t is the independent variable. So, but anyway, notice this is very obviously separable. Again, because of the multiplications. See if you can do it yourself. Give you a head start. I'm going to take a look at your assignment while you're getting a head start and kind of see if I've got some examples that'll help you. And by the way, the directions in the book will say, solve this equation. That's the way they word it. And problem 7 through 16, solve the equation. Well, it is an equation because there's an equal sign. It's just that it has a derivative in it. But it's not obvious what that means. Like, what are you talking about? Solve means get rid of the derivative.
Is this section for next week's homework?
Nope. This is today's.
Okay.
No, and this is good timing because you have this is gonna challenge you a little more just because it's asking you to take integrals, and it's been a couple of terms. At very best case scenario, it's been 6 months since you took complicated integrals, and so that's going to be part of this.
I'm looking at the homework due dates, and section 2.2 is part of homework 2, which is due the 21st.
Right. Yeah, it's not due. The 1.2, 1.3, 1.4 is due today.
Yeah.
So it's not due for a while, but it's today's discussion. Yeah, I see
Gotcha.
what you're saying now. It makes sense.
Gotcha. Thank you.
Yep, good question.
Made me panic a bit.
Yeah, so make sure you're looking at the syllabus. That's good that you pointed it out, because you all should be going into my open math today and attaching your work for 1.2, 1.3, 1.4, and then I'll post, probably tomorrow, I'll post all the solutions for it. I'll write myself a note to do that, or I won't do it.
I'd like to talk maybe after class today about yesterday's homework. I couldn't get Excel to do what I wanted it to.
Absolutely, yeah. So let's see, if I multiply both sides by x squared, then that looks good. If I multiply both sides by t, or dt, I mean. So it's clearly separable. In other words, I was able to separate them. But now the question is, can I take the integral? Well, you should look at the left side and say, oh yeah, that's easy. That's just power rule. So that x squared would grow an x cubed, and then I would divide by 3 or multiply by 1/3. And again, technically there'd be a plus c there. The other side though, not so obvious, right? Can you still survive that?
It's just a U sub.
Yep, it's just a u sub. And that's not obvious. It's been a while, but there's junk over the top of junk, which remember, the going forwards, when you took a derivative of a fraction, it was quotient rule. It was really involved and complicated. So when you see a fraction, that's not good. But if you switch colors, if you let, say, u be equal to 1 plus t, then that also means that du, the derivative of u, would be equal to the derivative of t. So I took the derivative of u, and I just wrote du, took the derivative of 1, 0, took the derivative of t, it's the derivative of t, which means the dt and du are interchangeable. And so what does that mean? Well, that means I could replace now this t on top with, well, what's t equal to? If I solve that for t, it'd be u minus 1. And then on the bottom, I would just have the square root of u, and then I replace the dt. Since these were equal, then I just replace du with dt. Is that any easier? Does that substitution make that problem any easier?
Yeah, because then you get two integrals. Because
Yeah,
you can divide by square root u.
that's right. The key is, from Calc 2, we don't like plus signs on the bottom of fractions, but we don't mind them on the top because you're actually free to divide them individually. In other words, this is just distributive law. This says both of these things up here are divided by this. Well, then you can actually divide them now, since there's only one on the bottom. So u to the first divided by u to the 1/2 would be u to the 1/2. 1 divided by u to the positive 1/2 would be 1 times u to the negative 1/2. In other words, effectively, that just got rid of the fraction, and now it's just power rule. So how does power rule work? You add 1 to the exponent, so 1/2 would grow to 3/2, and then you divide by that. You add 1 to negative 1/2, it becomes u to the positive 1/2, and then you divide by whatever that fraction is. And so that'd be 3/2 u to the 3/2 minus 1/2 u to the 1/2.
I think it would be 2/3 and 2.
Yeah, you're right. I got excited there. Yeah, that
It's
inverts.
the exact same thing.
Duh. Thank you. That's a duh. Yeah, you're dividing by a fraction, so you multiply by the reciprocal. And again, but that's one of the reasons, like if I was by myself, I might have accidentally made that mistake. How would I catch it? Well, I would go graph the original differential equation right here, and then I would graph my solution and they wouldn't agree. And I would know something was wrong and then I would catch it. Again, I would be thinking to myself, is my mistake a dumb mistake or is it something important? In my case, it would have been a dumb mistake. But you should catch those things yourself. That's my point. So, okay, mission accomplished. Now I just have to put t back in. So let's go back up here and do that. So basically now I'm just going to replace u with 1 plus t. So I'm going to just rewrite that now, except have 1 plus t in there. So I've got 2/3 times 1 plus t to the 3/2. And I've got minus 2 times 1 plus t, the square root of that, or that to the 1/2. And this also has a plus c on that side. And again, I could call it c1 and c2. But to clean things up, I will say I've got 1/3 x squared plus, I'll put the c on this side for no good reason. And just rewrite the rest of that. So again, mission accomplished. You got rid of the derivative, you're done. Could you clean things up? What's some good things you could do to clean things up here a little bit?
You could
What's
combine
one?
constants and multiply by 3. You in your solution you wrote x squared instead of x cubed.
Thank you.
You might be able to factor out a 1 plus t to the 1/2 if you really wanted to.
Yeah, that's a possibility. Good point.
But that kind of
Factor out a
feels-
1 plus t to the 1/2. That might make it clean up a little bit. Certainly multiplying both sides by 3 would be good. Does
and
this
I
make
guess you
sense?
could root it.
Yeah, you got to be careful with the minus sign though. If you square root both sides, because there's a minus sign, that doesn't work so good. Like you can't actually square root those two right sides individually. You have to just put a square root over the whole thing and it actually doesn't help.
Oh, you're right. So it wouldn't do anything at all except just isolate x. Yeah, I saw that 3/2 and wanted to get rid of it.
Yeah, that's tempting. Anybody bothered by the fact that the constant didn't get multiplied by 3?
It's just a constant.
It's a constant. So, again, it might be better form to call this C1 so that you distinguish the fact that this is now a different constant, something like that. But that's probably a better answer, isn't it? Isn't that a little cleaner looking, a little nicer? So some of your book questions just say solve the equation. Well, there it is. I just found the family of solutions for this. And again, most of you would look at that and say, I've never seen that graph before. I have no idea what that looks like. But again, let's go play with it a little bit. Don't miss the point of everything we've done. Let's go back and
The solution looks more complicated than the problem.
no kidding. So let's go back and take a quick look at this. Let's see if I shared screens properly here. I don't think I have. I gotta share a screen. Let's just slow down a little bit. Enjoy the process. So notice this says the slope is a function of x and y, which means I have no choice. And now I'm really going to be confused because notice it's x's and t's. So let's see, what am I going to do? Well, I'm actually going to call x y. So I wish that this had been 2 different letters. If it hadn't been x and t, it was like g and t, I would have had no problem at all. But now that it's x and y, except for they're switched, it's like that's really annoying. So let's see, it's t over x squared. So that t would be the x. So it'd be x divided by, it's going to be easy to screw up, divided by y squared. So my x is actually y. And then that's also divided by the square root. Let's see, that's the first time I've ever done this before. I wonder if SQRT will do square root or if I just have to type raised to the 1/2 power. Might as well find out now. 1 plus t, and that was our independent variable. So that's actually an x. Does it like that? Does it like square root? Oh yeah, look down here. It tells us that that's what it interpreted it to be. So now I'm pleased.
Hey Doug, out of curiosity, why wouldn't we just make t y and keep x as x?
Let's see. Well, you just got to be careful because the x is the independent variable. I'm sorry, in our original problem, dx dt, t is the independent variable and x is the dependent variable. And so notice this says dy dx, not dx dy.
Oh,
So I
okay.
actually think I have to do what I did.
Okay.
How come some of the graph is missing? Where's the rest of it? It usually shows like, how come there's none over there? You should be able to tell me that. Look right here.
Hey, square root of a negative number.
Can't have a square root of a negative. So x can be -1, but it can't be less than that. Notice that's exactly where the graph stops. Again, this is why I give a few questions in the assignment instead of 30 questions. Like you should stop and think these kinds of things. So notice this is a really kind of a fun looking graph. Notice it's got some verticals in it, so it's freaking out. Do you see that that's not good right there? That's freaked out. It's not working. See the verticals, all the verticals running right along the x-axis. So unless you're up here, as soon as it hits the x-axis, it's wonky. So notice this is an example of one that's not all that great. It's kind of hard to see what's going on. But that's kind of fun right through there. Isn't that one of the funnest locations? You see how it kind of comes down and curls down there, if you will, and then takes off again. That's kind of a fun location. But of course, what I'm interested in is, does the Desmos version of this graph, show any similarity to that? So let's see in Desmos, I think we said we could get away with just leaving the X's and T's in it. So actually, I don't think that does work if it's implicit though. So I think I'm going to stick with what we did before. I'm going to stick with the same X's and Y's. So X was actually Y cubed.
If you defined the variables, it might work. But I mean, that's kind of, you don't have to do that.
You're correct. X plus 1, it was 1 plus X, but whatever. And I don't want to type a fraction, so I'm going to call 3 halves 1.5 plus, oops, that was minus 6 again times 1 plus a t or x plus 1. And that is raised to the 1/2 power. And so again, an equation here that I've never seen before, right? This is crazy. And so I have no idea what this is going to look like. And when I see that, I immediately think, awesome. Isn't that exactly what it looked like? Didn't it kind of do that? That's the one I left and said it's really wonky. How come it stops right here?
At -1.
Yeah, it's hitting -1, right? So that's what happened over here. It just stopped right there because it hit -1. So that actually makes sense, doesn't it? So that's kind of fun. So do you see how that kind of verifies it actually worked? Crazy graph. It's pretty sweet.
It's interesting how a lot of the solutions are really interesting, kind of in a radius
Yeah.
around the origin.
Yeah.
As they go infinity, they just kind of lull.
And you can kind of see this happening, right? In other words, this comes down. If I just look over here, don't these kind of come down and then they kind of create a curve? They're sort of curving and then they come back up again. By the way, Calc 4 addresses this as well, this concept, because it sort of looks like weather. And so does it make sense that right here is acting like, if you will, like I said in the language, common sense language, the other day, kind of like a planet, like it's all the particles are trying to curve around the origin in a sense. They seem to be aware the origin is an important point in this particular solution. So that's just kind of cool to think about. And then of course I see that happening here as well. So very fun, just super neat stuff. Let's see. So then the next set of questions, and maybe I'll just pick one of these. The next set of questions in the book says in 17 through 26, solve the initial value problem. It doesn't say solve the equation, it says solve the initial value problem. So what does that mean? Well, that means they're going to not just let us stop. They're going to make us, go on and find a particular solution. In other words, figure out what C is. So let's pick another question to do. Seem to be struggling here. Try that again. And at a glance, some of these look pretty terrifying. I don't know if you should pull up the 2.2 assignment. It's on page 43 in the book, either in my open math because I posted it for you, or because you have the actually correct book. But I'm just going to pick some random one in here. Let's do 23. What's the deal? How come this isn't sharing a screen for me? So start 23 if you actually can see it. And I will catch up whenever my computer lets me. I'm not a patient person, so I'm going to give up and try this again. There we go. Question 23 says solve the initial value problem. And we are given t to the -1 times dy dt. I don't mind that one because y is in its usual location. And I never mind time being the independent variable. So this one feels far less painful to me. And then they go on to say y of 0. I'm glad there's a 0 there. At times 0, it's pi over 4. Again, I just want to give you a second to try to make some of your own progress with that. Because it's in this section, it implies that it's separable. You should be a little terrified in your vague memory of seeing a squared trig expression. Oh no, I'm going to have to take the integral of something squared. This is not good. All right, catching up. So let's see, t to the -1 is really just 1 over t. So it's like t is on the bottom. So I guess I'm going to end up dividing cosine squared y over to this side. And I'll leave the 2 on that side because if I bring it over, it's 1/2 and I don't like fractions. Then that means the t on the bottom would multiply over, and so would the dt. Sure enough, that's separable. What did you do? What do you do? Turns out this was nice. Whoever wrote this book was nice. They realized it's been 6 months and they don't expect you to be an expert at integrals. How do you handle that trig expression? Did anybody navigate that beautifully?
Secant squared is just the derivative of tangent.
Yeah, 1 over cosine squared is actually secant squared. And I posted on my open math a table of integrals. At this level of math, I don't want this class to be, I never want you to have a really hard integral to take. Generally speaking, in this class, the integral taking is not the point. And so to resort to a table of integrals where, you know, somebody's already done this for us is not a terrible thing. I guess on a test or something, I would either, I'd like to try to keep the integrals simple so that you are doing them yourself.
No
But
trig
yeah,
subs.
but in this case, yeah, I mean, let's avoid trig sub. I mean, it's good practice and so forth, but that might come up in the assignment. I'm okay if it does. But fortunately, the derivative of tangent is secant squared. And so the integral of secant squared is tangent. So fortunately, this isn't really hard at all. And the integral of 2t is t squared. And so again, it's plus c on both sides, but I'm just going to give it to 1. And again, notice I get an equation that I've never seen before. It's like a combination of tangents and parabolas. And so no wonder I'm going to get some kind of a weird expression. But then this was not just a family of solutions, but an initial value problem, a particular solution. And so they're saying, hey, if you plug in t is 0, then I'd like to get y to be pi over 4. Oh, I see now why they chose such a weird number. Why didn't they say y of 0 equals 6? Well, that's because the tangent of pi over 4 is something I can look up on my unit circle. And again, I posted a trig, kind of a trig cheat sheet on my open math for you as well. So you shouldn't, maybe some of you memorized what the tangent of pi over 4 is. I happen to remember pi over 4 is 45 degrees, and tangent and a 45-degree triangle, the opposite and adjacent are the same side. So I think the answer to that is 1. So that means I end up with 1 equals 0 plus c. So c is 1. So now I have tangent of y equals t squared plus 1. And that, I think, is the solution, the particular solution to my initial value problem. And these are always particularly nice because then not only can you kind of go back to the plotter and so forth and kind of check it, but you can go to Desmos and not just put C in there, but put 1 in there and kind of make sure they're an exact match. And so again, you should be doing this every time. You should be doing this on your test. So let's do it here as well. So if I go to GeoGebra, let's see, the original problem was t to the -1. I'm just going to put, notice I don't have a choice. I have to put that on the other side. So that would be 2 times t, except for I don't get to use that because it says it has to be a function of x and y. So it's 2 times x times the cosine squared. I wonder if it lets me put squared here. I don't know the answer to that as well. Squared of y. Let's see if it'll understands that. Notice it did. It did understand that. Kind of fixed that for me.
I don't think we can see it, or it might just be.
I think it's my fault. Yeah. I think I'm sharing the wrong screen. I'm still sharing the other screen. So thank you for speaking up. There we go.
Gotcha.
So I actually put the squared in the cheat location. I was thinking I might have to put parentheses around cosine y and put a squared there, but it let me do that. And I love that this particular one, it tells you down below, like you type something weird up here, but then it shows you what you think you typed. So I'm pleased. Now we need this thing to go through 0 pi over 4, and this is the place where pi over 4 is kind of unfortunate because I don't really know what that is. And so it's 0.785. Let's see, and I don't think there's any way to type that. I wish there was a way to type that in, but I'm going to 0.785. But that's okay. I'm just using this to check my work, right?
If you double click on the point, I think it brings up a box that you can type
Yes,
point.
is that true? Oh man. How did you discover that? Like pi as a word. Maybe it will, maybe it won't. It did. Nice job. Down here, probably there's, my dad always gets on me about that. I never read the directions.
Those are what you read after you've already opened the thing and tried to set it up yourself.
Right. So now, of course, I want to go into Desmos and see if my particular solution that I got, and again, I'm very happy to be able to just type it in as a implicit equation. I don't even have to solve it for y. Of course, that's not hard. I could say the arctangent of t squared plus 1. And I think in this case, I can just say, I can use t. I don't think it's going to mind that. Notice it did. What does it say up there? It says, we only support implicit equations of x and y. So it's like, nope, sorry, you can't do that. Thankfully, though, it told me that, if you will. So that's kind of weird. So first of all, notice that's the solution we just got. Notice it's actually working. But yet there's all these other solutions. And again, that's a surprise to me. My first thought is like, huh? What's the deal? As far as checking my work, I'm done because this is definitely the graph we just saw over there. But what are all these other answers? Anybody have any good thoughts on that?
Tangent kind of just does that. Like it's a sine and cosine function combination, and those are oscillatory functions.
Yeah, remember tangent actually repeats itself. In other words, if you took the tangent of 10 degrees, that's exactly the same as the tangent of 370 degrees, because 10 and 370 in the language of mathematicians are coterminal. They terminate at the same location. So, oh yeah, I guess that makes sense. And you may also remember that tangent repeats itself every 180 degrees or pi. So notice that's exactly pi above the other one. So every pi that I go, I'm getting the same exact graph. So that doesn't mean we were wrong. It just means there's actually more answers to that.
It's really fun to drag the slope field plotter around because it goes to a different area. It's like,
Yeah, notice there's much funner answers to this than the one we got. Like that's kind of a cool one. Oh yeah, I see what you mean. In other words, it actually is showing all of them.
Kind of flops to a different area and kind of sticks there.
It's pretty cool. Nice. Isn't this awesome? Isn't this amazing? What a world. Let's see. So we've done some examples pertaining to your assignment. We've done some examples that are pretty similar to, actually out of the books. I think that'll help you be successful. So we've got up through question 22, but then there's 34 and 38, which kind of jump into the word problem version. So I want to play with those just a little bit. 34 is just a wonderful question because it deals with Newton's law of cooling. I'm not going to do this one, but it's, a second ago when you guys were doing your problem, I got up and stuck this coffee in the microwave because it's got cold, and kind of the mathematics of, how this cup, I put hot coffee in it when I bought it at the store, and, then it starts to cool off. And of course it's a function of the kind of cup it's in. It's just in a paper cup, so it cooled off really fast. And but it's also kind of a function of how warm the coffee is and how warm the room is. Like I'm in an air conditioned house, it's like 75 degrees and the coffee was 120. But if I was outside and it was 100 degrees outside, it's going to cool a lot. It's going to cool kind of at a slower rate. Does that make sense? But again, it's what we got at before. Just like the river drops down, what's this coffee going to do? If I buy it at 120 degrees and I bring it into this 75 degree room, it's going to work its way exponentially. It's not going to go straight there. It's going to work its way slowly. And it's going to take a lot of time for it actually to make it to 75 degrees, but it'll get there eventually. So it doesn't just race to 75, it levels out, it asymptotically approaches 75. And so Newton's law of cooling is really cool. And you can also appreciate it's kind of an important, it's important, you know, just sort of in a playful sense, like, you know, how long can I wait before I don't know if you're like a snob like I am, but I like warm coffee. And when I, you know, cook meat on the barbecue, I want it hot. I don't want it all went out. But then there's also very monetary or economic versions to this too. I got a friend that works in a job that involves chemistry, and they're always kind of putting coatings on paper to make film for diagnostic equipment for medical reasons and so forth. And you know, the temperature of the chemical process is really important. And so they're having to pay attention to those kind of things at his work. And so just understanding the dynamics of, you know, things that are going to heat up and cool are, you know, it's kind of a powerful application. So that's kind of a neat one. So I'm not going to do that one, but I am going to do one kind of like near it, I guess you could say. And it's also, this is a bit of an introduction to something that's coming next. But so it's kind of like question 33. Let's see, do I actually want to? Yeah, I think maybe I'll actually even kind of do one like 33. So this is a practical problem. Practical in the sense that you don't get an equation, you got to write it for yourself. And so here's what I'm told. I have this tank. And what's happening is 10 liters per minute of liquid are going into this tank. And I'm told that 0.3 kilograms per liter are, they're saying salt in this case. So that should kind of make sense. And again, this is kind of neat because this is, if you will, the mathematics of mixture. And I mentioned this a little bit the other day, but mixture with respect to dropping chemicals into something. So this is like somebody looking at a pool and saying, okay, I want the pool to have some salt in it. So 10 liters per minute of liquid, like water, going in, and then that water has 0.3 kilograms per liter of salt in it. And so I'm basically adding salt to this tank. Now, what's in the tank right now? Well, if the tank is really salty, does it make sense that's going to dilute the tank? If the tank is just pure water, then this is actually going to increase the saltiness in it. Does it make sense if we just let this run forever, that eventually this tank will be 0.3 kilograms per liter, no matter what it was? Remember our differential equations when we drew the graph, when we drew the direction field, it always ended up exiting the stage kind of in the same location no matter what. Well, this is why. That tank is going to get to 3.3 kilograms per liter no matter what it is right now. Did it start at pure water? Well, then it's going to increase to 0.3 kilograms per liter. Did it start like solid salt? Well, then this is going to dilute it down, but it's going to eventually end up at that level. That's kind of the idea. So, okay, and we're also told that this is a 400 liter tank. That's its size. That's how much liquid it holds. Of course, liquid's pouring out of the tank too. And we're also told that the amount in the tank at time 0 is 2 kilograms. So this is an initial value problem. We don't want a family of solutions. We want a particular one. So right now there's 2 kilograms. Is this tank really salty or not very salty relative to what's coming into it? Anybody have a take on that? It's okay to be wrong.
It's like a little over 10%, right?
Well, notice it's 2 kilograms. per 400 liters, right? That's what's in the tank. Okay, so 0.3 kilograms per liter would be 3 kilograms for 10 liters. Oh, this is almost pure, like there's hardly any salt in it. And this is pretty salty. Does that make sense? So it's actually pretty low salt in the tank right now. So this is like somebody saying, hey, this, you know, tank needs more salt in it. So let's pour some liquid in that's higher salt. So it's going to increase. So this is a mixture problem. And this is super, super practical. And, you know, like in my house right now, it's 100 degrees outside, or, you know, will be later or whatever. But, you know, your air conditioner might be pouring in air that's, say, 75 degrees, and it kind of mixes around. And so, you know, it's like a fight between the air that's trying to infiltrate your house and the air that's actually coming out of your air conditioner. And so this mixture idea isn't just kind of salt in the pool, it's air in a room. And it's got all kinds of kind of implications for that. So if I introduce something different, you know, we're always kind of listening to environmental kinds of things. And if somebody, you know, sprays hairspray or something like that, well, now that starts mixing with the air in the room, right? Or it mixes with the air in the world. And so how does that change? The point is this tank is changing like crazy. Does that make sense? This whole tank is just changing like crazy. And of course, what you really want is, practically what you want is to stop at a certain point. In other words, I want to get to a certain place and then stop. But of course, it's just kind of increasing over time. So this is kind of a neat problem. Well, how are we going to get some kind of an equation for this? Well, do you see that everything we know here is about change? Like that's the only thing we know. Like we're sending a rate into the tank. Well, that's a rate of change. That's a derivative. And then the rate in the tank is changing. And so this is just very confusing. And ultimately what we're after is, how is the amount notice the A is actually equal to the number of kilograms of salt. It's not a percentage. Notice we're told A of 0 is 2 kilograms of salt. So A is literally the kilograms of salt. So the change of the kilograms of salt over time, that's kind of what we know things about. Well, notice there's kind of an in and an out to this. So dA dt, let's think about that for a second. What would the units of that be? dA dt. What's the unit of that?
Kilograms per second.
So A is the amount of kilograms. That's why I wrote it down. And then T is time. Do we know what the time is? Is it seconds, minutes, hours? Do we know anything about that? Nothing in what I wrote shows that. Yes, we do. We do know, don't we? Right there. Minutes, liters per minute. So that means this is kilograms per minute.
I was wondering if that M was minutes.
I didn't think we did, but. So yeah, the problem in the book says MIN for minutes because that looks like meters. So they put MIN as they should there. So does it make sense that this would be, the change in the tank would be the rate in minus the rate out? That's not obvious, but that's kind of where our equation is going to come from. And again, notice what's hard about this. In the real world, no one's ever going to do what we did here. No one's going to walk up to you and say, you know, in the real world and say, can you help me solve this? Somebody's got to write that equation. This is just, you know, playful practice, if you will, but this is not playful practice. This is practical, but there's no differential equation here. You got to make it yourself. Well, what's the rate in? Well, notice the rate is kilograms per minute. This is very confusing. You might say it's 3 kilograms per liter, 0.3 kilograms per liter, but it's like, that's not the rate because that's the wrong units. It's got to be kilograms per meter. Well, notice though, if you take 0.3 kilograms per liter times 10 liters per minute, notice the liters cancel and you do indeed get kilograms per minute. So this is actually 3 times 0.3 times 10 is 3. So it's 3 kilograms per minute just of salt. stop and think about that. Does that make sense to you? Because we're really talking about the rate of change of salt in the tank, right? Not the rate of change of liquid, but the rate of change of salt. That's why I went to the trouble of writing out what A is equal to. It's not liquid, but salt. And so if it's 0.3 kilograms per liter, but then 10 liters a minute are coming in, then I guess that'd be 3 kilograms per minute. Okay, that makes perfect sense. So that's the rate in, but what's the rate out? Doesn't that seem really like, what? I don't know anything over there. It's just like water coming out.
Well, depending on how we decide to model this, it could be really complicated, or we could just assume that as soon as the liquid enters in, it instantly becomes homogeneous.
Yeah, Landon makes a really good point. In other words, when it came in, if all the salt kind of hung out over here, like think about river coming into a lake. If something weird is in that river, like isn't all that stuff going to hang out near the river? It's not going to be like a mile down the other side of the lake. So we do need to assume that this is kind of instantly mixed up, which if this is an industrial application, there probably would be some kind of a blender in there to be mixing it on purpose just to make sure that actually happened. Because you know, if this liquid was going to be used for something, we would need it to be homogeneous, like Landon said. So that's a good point. So we're going to assume it's mixed instantly.
So in the book, it has 10 liters per minute out as well. So would we do 10 liters per minute? Oh, never mind.
Yeah, no, you're going the right direction. In other words, you have to decide, is it going out the same? And in this, it's saying it is. And so that's something that is given in the book that I didn't add to this. So I'll add it now. But does it make sense? It doesn't have to be flowing out at the same rate. It could be flowing out at 5, which means the tank would actually be filling up, which of course, if it's closed, wouldn't be good because that's not going to work. Or it could actually be flowing out at say 18 liters a minute, but then eventually you're just going to run out of water in the tank. So the kind of the most natural thing to do is to have it flow out the same as it's flowing in. What we need to set up here then is kind of the same thing that we did here. In other words, we have 10 liters per minute, but we're going to have to multiply that by kilograms per liter for this to work. Well, notice that there are 400 liters in the tank. Isn't that how much liquid's in there? How much of it is salt? Well, A of it is salt. A is, that's why it's kind of important we did this, A is the number of kilograms of salt in the tank. Now it started out at 2, but does it make sense right away it's going to go up, up, up because we have saltier solution coming into the tank? So you actually have, since the L's cancel, you have 10A over 400, or I guess that'd be 10A over 400, or I guess that would just be A over 40. So the amount coming in was constantly 3 kilograms per minute, but the amount going out depends on how much is in the tank. Isn't that weird? Like it early on, basically 2 kilograms per 400 liters is what's coming out of the tank. But it's getting saltier all the time. And so that's what's kind of confusing. So in the end, we wrote our own differential equation. We're going to do a lot with this particular application. Now that I kind of have all the units sorted out, I'm just going to leave them out.
Is A over 40 kilograms over minutes?
Yes, because of back, just like this was kilograms per minute. This over here is also kilograms per minute. So it's all kilograms per minute. So dA dt is kilograms per minute. This is 3 kilograms per minute. This is A over 40 kilograms per minute. So we can actually add them all together. So it's pretty tricky. Now the question is, and you know, we'll practice this more, but the question is, can you solve that now? Is that separable? Did they put this in the right section in the book? Your first reaction should be, oh, I see a negative sign, or you know, minus sign, like that's not good. Can you separate this? I'm going to give you a second to try to solve this yourself, and either succeed or fail. Newton's law of cooling is working hard on my coffee. It's not very warm anymore. Again, you might think, oh, I'll add a over 40 to both sides. But that's a bad move, because then when you multiply by dt, then that a over 40 on the left side is going to be multiplied by dt, and now you got a's and t's. And so this is not obviously separable. I've given you a little time to think about that, but I'm gonna do a couple things here to at least make sure you're solving the correct equation. So what I'm going to do to start with is I'm going to multiply top and bottom of 3 by 40. So I sort of have a common denominator, so I can actually add these fractions. Maybe now, looking at it that way, maybe now you see a little better. But what you would have to do is divide both sides by 120 minus a. And you could either leave the 1/40th on the other side, or you could bring it over too. You could put the 40 over there. 40 is a constant, so it could kind of go anywhere you want it to go. But I think I'll leave it like that. It's not right or wrong to leave the 40 on the right or the left. It doesn't really matter. But sure enough, it's separable. But you got to be very careful with minus signs and plus signs. If you didn't make it to there, again, I'll give you a second here to try to take it a little further. Remember, this is an initial value problem because we knew that a of 0 was 2. So try to actually get the entire correct equation for this. And let's try to solve it explicitly for a. Let's find a as a function of t so that we can actually use this to find the amount of salt in the tank. Such a neat problem.
Could you perhaps pull the initial conditions up again so I can write them down?
Yeah, I'll just write them right here. A
Okay.
of 0 equals 2.
Thanks.
So the integral of 1 over junk is the natural log of the junk. The integral of 1/40th with respect to t is 1/40th t. And both sides would get a constant. but there's one small mistake in that. Does anybody know what it is?
You need a negative in front of the natural log.
Why? Like, how'd you know that?
Because in order to take the integral, you had to do a u sub, and the derivative of 120 minus a is -1.
Yeah, it's a little safer to do what we did earlier and say u equals 120 minus a, but stop and think of it backwards. If you took the derivative of natural log of junk, isn't the derivative of natural log of junk 1 over the junk? But then don't you have to multiply by the derivative of the junk? And since a is negative, the derivative of a would be -1. So notice there's a negative sign. So it didn't work. It didn't give us this answer back here. Well, it would if we had a negative sign. And so if you're a little more careful and let u be 120 minus a, I'm going to erase this, but if you let u be equal to 120 minus a, then you would have said du equals -dA. So when you replaced dA, you would have to replace it with -du, and that's where the negative came from. And so that's kind of tricky. So this is actually negative. Now again, we got it. We could kind of work it right now. But I'm gonna solve it for a before I plug in that a of 0 equals 2, although I could do it right now, but I just don't want to. So let's see, I'm gonna get rid of that negative first. So I have natural log of 120 minus a equals -1/40th t. And I could say minus c, but remember this is just a new c. So what I usually do out of laziness is kind of go, oh, this is a new c, but I just want to leave it positive. So I'll go back to the original one and make it c1. And so then I say, okay, well, now I can get e involved. Natural log of the e to all of this stuff. And it's just cooler. It doesn't matter where you put the c, but it's actually just cooler, as I said before, to write it this way instead. And the same thing happens. In other words, if I go back and say, okay, now this is sort of C2, then I'm going to rename this C2 just C. So I'm going to call this C times e to the -1/40th t. Do you need to do that? No, leave the c up in there in the e. It's just nicer to put it down. And again, notice what this is looking like is, well, it's just like the river thing. It's when things change by a percentage, this is the type of equation that they yield. So now I can solve for a by adding a to the other side. So that leaves 120 on this side, and I have to subtract c e to the -1/40th t. And so a would be over here. And again, I could write a as a function of t. That's kind of cool. So I'm basically there. And so now I'm going to plug my constant in. So when t is 2, a would be 0.
Hey, Doug.
Sorry, when t is 0, a would be 2. Go ahead.
I got a slightly different answer, and I can't quite see where I went wrong, but I did do something differently at the very beginning, and I just, instead of finding the common denominator, I just divided by 3 minus a over 40.
Yep,
And then
that's okay.
when I integrated that, I got -1/40 times the natural log of the 3 minus a over 40. And then when I did the algebra to get to my...
Okay, wait a second. So you did what? You got to here, and then you did what?
Sorry. Well, then I integrated, and I got
Okay.
-1/40th. I just got the difference is instead of getting -1/40th t raised to the exponential, I got a -40 t. And I can't. So okay, so I got here, and then I have a plus c too.
Yeah.
When I undid that, I did e to the -1/40th of the natural log of 3 minus a over 40, which then gave me 3 minus a over 40 raised to the -1/40th power.
So well, if you move this to the other side, you're going to end up with 40 there, right?
Right. And that would still yield the same answer. So because ultimately I ended up like reversing it, like putting it to the other side using the root. So then if we raised it to the exponential, then it would be 3 minus a over 40 equals e to the negative 40t.
That's correct. Yep.
So, but that's different from what you got.
Yeah, I see what you're saying now. Let's,
But
I mean, they will be the same ultimately, or perhaps you or I made a math mistake, but let's figure that out in more detail after class. If it would have been easy, I would have just answered it right then, but actually I'm not sure.
Sure, no problem.
My thought right now is like, I'm not sure what's going on there. That's kind of bothering me.
Which is why I asked. I didn't
Yeah,
mean to.
fair enough. I'm glad you did. And again, that's what I want you all to do in this class. I'll either answer it right away, or I'll say that's a big question, or maybe I'll just think, well, that's your question, but other people aren't really going to care about it. So then I'll say, let's do it after class. But please just interrupt and like say it immediately. Let's talk about it. If I think it's instructive to everybody, then I'll point it out. And that's exactly why I did that just now, because there's nothing, like, why did I choose to do this? That's probably none of you would have done that. And I'm not even saying that's like the best choice. That's just what I happen to choose to do. And so you will get different looking answers, but they still should behave the same in the end, or you made a math mistake, or I made a math mistake.
Thanks for taking the time to look through it.
Yeah, that's wonderful. So let's see, if t is 0, then that means, seems like it's time to change colors. That's 1. So I end up with 120 minus c equals 2, which means c has got to be 118, I guess, right? So now I think I have my particular solution. This is very exciting. And so I usually write the a on the left side. And so now I'm saying, and so now I've got my model. And again, do you see the power in this? Because now I have the power to tell you how much salt is in the tank at any time I want. That's amazing. That's just super cool. Now, I'm not sure I haven't made a math mistake. And so let's do what we've been doing, which is quickly go back and check to see if we got this right. So share the screen, bring up our slope field. Bam, 3 minus a over 40, but a was our dependent variable, so that was y. I think this is a case where, a lot of time is going to pass. So I think I need much larger. I'm going to try 20. I don't know if that's a good choice, but I'm just making that up. I think I need a much larger screen to actually see what I wanted to see. It just looked like a line to me there. And I was thinking that doesn't make sense. And so notice now that I see that curve, I realize it's even kind of worse than that. So I'm going to try 90. These things are good to do live, and just to kind of help you think them through. Maybe that'll work. Take it out to 190 just because out of laziness. I think that'll be easier to type in. There we go. Now, somebody tell me, why are you not surprised to see and watch as I drag this around? Do you see how it's exiting the stage to the right? Would you agree it appears to be exiting the stage to the right at 120? Can somebody tell us why that's the case? Why is it exiting it at 120 no matter where it started? Think about the fact that 0.3 kilograms per liter of salt was coming into the tank.
Is that the limit of the saltiness, I guess?
Yeah.
Like eventually
right.
the tank will just meet a limit and it can't get any saltier as long as the conditions stay the same.
That's exactly right, Connor. What's coming in is 0.3 kilograms per liter, right? And so isn't that what the tank's going to eventually be? 0.3 kilograms per liter. Well, how many liters were in the tank?
400.
400. If you take 0.3 times 400, you get 120. So eventually there's going to be 120 kilograms of salt in the tank. So that's actually not a surprise that it asymptotically is working its way there. Now we said at, thanks to Cheyenne, we said that at time 0, we had 2. We agreed earlier that that was not very salty, right? So that means it was actually increasing in saltiness. So it started out there and then it worked its way up to 120. Now in the real world, does it make sense? Your goal might be to say, I'm going to pour this salt in, but what I really want to do is turn it off when it gets to 80. Does that make sense? I want it to get to 80 kilograms of salt in the tank. And so then we could solve this and say, oh, look at that. It's like 45 minutes or whatever. Oh, you know, we might not just want to let it go forever. We're turning it off at some point. You know, the pool got to the right amount of chlorination. And so that's kind of powerful. So there's our graph. And of course, we're over here in Desmos now thinking, since we solved this explicitly, then we should actually just be able to type it in like it sits. So we say capital A equals 120 minus 118 times E raised to, not D, E, raised to the negative 1/40th T. So would that be negative T divided by 40? I'm just going to be a little lazy. So, okay, good. It went through the 0.12 and then, you know, look at that. It's asymptotically apparently leveling out at Y equals 120. Yeah, look at that. So does that make sense? I got it right. I know I got it right. And so it's working its way slowly. Isn't that interesting? It doesn't just go straight up and just as a line and just bang into that. It works its way up to it really slowly. Can you feel that that's exactly what would happen? It's not going to just get there quickly. Notice you go way out here and it still hasn't made it. Does it make sense this is actually an asymptote? It's actually never going to make it, theoretically. You understand that? Theoretically, it'll never get there. Practically, it'll be close enough, you know, a long time ago. Like I might look at this and say, you know, you're pretty much there after 200 minutes, close enough, 200 minutes, you're there. But if we got here to 550, still not there. I guess we can't even see that. Yeah, we can. There we go. Still not there, but ridiculously close. Look at that. Notice it's within 1/1000th over here. So it's kind of, but isn't that what calculus is about, is limits and so forth? So you, in a sense, shouldn't be surprised to see that. So notice I know now that I'm correct and I didn't screw this up. It's a match. But I think what's so beautiful about this family of functions business is that what this is modeling is this is 0.3 kilograms per liter of salt coming into the tank, but it depends on what's in the tank to start with. If I was over here at 200, then that would be like you started with 200 kilograms of salt in the tank. Woo, that's really salty. And in this particular case, you're diluting it down to 120. But you see how this is kind of cool because it matches everything. So it depends on what the initial condition actually is. It's just a really powerful concept. How's your brain? Is it hurting?
Yep.
Should be a little bit. This is kind of neat stuff. But you're, again, I want to encourage you by saying you've done it all now. Like this is what differential equations is. All we've got to do is kind of just, you know, play around with how to solve different differential equations. And but you're seeing the big picture now. And it was only 4 days ago that you never even heard of this. So your brain should be hurting a little bit, right? So I'm not really going to be teaching you anything else. And I've got to show you a bunch of techniques and they'll cause your brain to hurt too. But it really just comes down to I've got to solve a differential equation. And so how am I going to do that? Well, right now you can solve it if they're separable. And that was kind of a cool application to see just because it, you know, we were able to write the equation for ourselves and it was separable. And so we were able to even solve it ourselves. But there are other ones we could write that we still can't solve because there's kind of harder things coming our way. And I could spend the next 5 weeks talking about applications now. There's all kinds of neat ones that pertain to this. And so, we'll kind of do a mixture of those things. I would recommend, even though, especially with this section, again, 2.2 is not due until whatever later in the week, next week, before the test. But do it this weekend so that you can come back and say, you're more than welcome to ask me questions after class, like 34 is an application about the law of cooling, and 38 is an application about a free fall. It's a really cool problem about how a skydiver reaches terminal velocity and so forth, and how it takes a differential equation to understand how fast you're falling, because you jump out of the plane and you're going 0, but then you start speeding up and speeding up and speeding up as you fall. And the key is the only thing you know is about speed, and that's why that's a differential application. Just dropping a rock. Next time you see anything fall, a bird flying through the air, it's a differential equation that actually models that gravitational pull on that object. And you might not be sure you got that question right, or you might get stuck. Well, that's why I'm not making it due Monday, because I want you to be able to stay after class Monday and say, this is what I got for 38. Is it right? Or I have no idea what to do on 38. Can you give me a hint? Like, there's time for that. And you should be asking me those things, because I didn't do an example like those on purpose, because I want you to see what sense you can make of it on your own. All right, get yourself out of here. We are going to answer David's question, though, because he did it slightly differently. We're going to keep talking about that now for a second. So if you want to stay on that discussion, you're more than welcome to. But make sure you link me your homework today, because it's due today.
Thank you, Doug. I might text you about some problems I might have on the homework later.
Okay, fair enough.
Later.
Later.